Hi, everybody. Today, what we're going to go through, you can see the title on the top. We're going to be producing some formal sketches today. So, we've had an introduction as to what the graph of an exponential looks like. We have in our mind the idea of when a curve is an increasing exponential curve versus a decreasing curve. And we also understand that that y-intercept is our hard turn, where our graph changes from going and slowly rising to rising very quickly, or vice versa in terms of decreasing. What we're going to do today is we're going to put everything together. That is, we're going to draw back on our understanding of all of our transformations, and we're going to go through and produce some formal sketches. So, what I've given you in that equation is almost as ugly of an equation as I could give you. I could have made the a value out of the front negative, but I don't think we need to revisit everything. We should have transformations pretty well understood. What we want to do is we just want to focus in on, well, how do those transformations affect an exponential graph? And then how do we produce the picture for it? What are the expectations? So let's take a peek at what we have in the equation I've given you, and let's make sure that we can nail down all of our transformations. So let's take it slowly. We notice that we have a multiply by 3 on the outside of that function. We know that if we multiply, that means that it is a stretch, and we know that if it's on the outside of the function, that means that it is a vertical stretch. So we would have a vertical stretch by a factor of 3. And we know that if we vertically stretch something by a factor of 3, we are going to make that graph steeper. Okay, now we jump up to inside the exponent, and we should be good to be able to interpret that -4. However, I think it is really valuable to you to stop for a second and recognize that that form of that equation is not written in a form that allows you to interpret all transformations. If we go back to Unit 1, remember that I need to factor out whatever my coefficient on my x is to be able to interpret my horizontal shift. So I need to factor out that -4 from both terms inside my exponent. So I factor out that -4, and then I'll get an x plus 5/4. You can do a little confirmation, re-expand in your 4. Notice we get back to the same thing. I've got my -6 on the end. That when I factored out that -4, now I can interpret my horizontal shift. So notice, since we're talking about exponential functions, inside means inside the exponent. Outside means outside the exponent, for us to be able to determine our vertical versus horizontal. Now we're in an instance where we can interpret that. Well, the first thing, let's interpret the negative. That negative causes a reflection. Now, which axis are we going to reflect it in? Because I'm on the inside, that means that I need to reflect it horizontally. And if I reflect my graph horizontally, then I'm reflecting it over the y-axis. Okay, now I can interpret the 4. That 4 is going to be attached by multiply, which means I've got a stretch. It's attached on the inside, which means that it is horizontal. So I have a horizontal stretch, and I need to recall that when I'm affecting my function on the inside of the function, I have to deal with the opposite operation. So it's a horizontal stretch by a factor of 1/4. Now I have to consider my slope. And if I'm going to make all of my points 1/4 the distance to the y-axis, I am making my graph steeper. Okay, now I can address that plus 5/4. I know that that's attached by addition or subtraction, so it is a shift. I see my plus in there. I know I've got to deal with my opposite operation, so I'm shifting it left 5/4 units. And then I have that -6 on the end. I can tack that on to that same shift statement because it's attached by subtraction, so I know it's a shift. And I'm going to shift it down 6 units. There we go. So we've got all of our vertical stuff in blue and all of our horizontal stuff in red. As I said, almost as ugly. All that could have happened was that 3 that I circled in blue could have been negative, and then we would have been able to interpret a reflection in the x-axis. Okay, we've got a little review then of our transformations. We also look and see how those look within an exponential function. What we're going to spend the rest of the time doing today is to go through and produce formal sketches. So let's take a look at the screen, look on your handout, and see the instructions for problem 2. These are going to be the same instructions that you're going to see on an evaluation, the same expectations. First off, the instruction says to sketch. When we sketch, we know that we need to have 3 features of our graph labeled. Those 3 features enable us to see where does the function exist and help us to determine the shape of the curve. I want you to notice the 3 features that we need to have labeled. The first thing that we need to have labeled is our y-intercept, always. The second thing that we need to have labeled is our transformed y-intercept, and we'll talk about what that is. The last thing is we need to have our horizontal asymptote. We need to have 3 features labeled on our sketch. So what I want to do, and I'm just going to get rid of that green a little bit because it almost overshadowed the equation of the function, is I want to go through the sketching process. Now, I'm going to ask that you don't copy this down yet because I actually want to go through the process that I would follow with you. But what I want to talk about first is let's address graph out. So what I mean by that is let's examine right off the bat that what we have is a graph that is based on the function y equals 2 to the x. And I should know enough by now that since that base is bigger than 1, then I would have an increasing curve with a hard turn at the y-axis. I know that every base exponential has a y-intercept of 1 and a really sloppy horizontal asymptote at y equals 0. We should have those properties in our head from last time. We know that. So what we're going to do is we're going to do all those transformations to it. So what I'm going to do is just jot down those transformations. Again, I'm going to ask that you don't get this down. So what are those transformations? Well, the first thing is I noticed that I would have a reflection in the x-axis. Like it's really sloppy. I'm just jotting it down fast. I also noticed that I would have a vertical stretch by a factor of 3. I told you I'm jotting it down really fast. And then we notice that we're going to shift it up 4. So all I want you to do is picture that purple curve reflected in the x-axis, vertically stretch it by a factor of 3, shift it up 4. I hope that we could maybe picture a graph that was this. Something like that, let's say. Really sloppy, but we've got that in our mind. Then what we would have to do is label those 3 properties. You can absolutely do that method But what I'm going to suggest to you is, how about we go through and we find those three properties first, and then we use those three properties to help us with our sketch. So what I'm going to do is I'm going to get rid of that whole big mess that I just put down. And what we're going to do is we're going to start with those three properties. So I think what we should start with are the easiest things that we can find. And I think the easiest thing that we can find right off the bat is going to be our horizontal asymptote. So I'm going to put a little heading there, just HA for horizontal asymptote. I want us to imagine doing all of those things to our base function of y equals 2 to the x. So I want you to imagine reflecting that curve across the x-axis. Okay, picture it. So we should now get the green curve. Now what I want us to do is I want us to vertically stretch it by a factor of 3. That should give us the red curve. Now what I'd like us to do is to go ahead and shift it vertically, shift it up 4 units. That's what we're doing as we perform those transformations. And I'm hoping that just kind of crudely doing what we just did, you can determine your horizontal asymptote. So again, I'm going to get rid of all of that stuff on our graph. And I'm hoping that we are good to come up with a horizontal asymptote at y equals 4. If you take a look, reflecting your asymptote in the x-axis does no change because it is the x-axis. Vertically stretching that has no change because it's on the x-axis. That the only transformation that will affect your horizontal asymptote is your vertical shift. So I can read my horizontal asymptote directly from my equation. Okay, the next thing that I would find is I'm going to find my transformed intercept. So I'm going to put down another little heading like TI for transformed intercept. What the transformed intercept is the location of the old intercept after it's been transformed. So if I put my purple graph down again, that represents just y equals 2 to the x. I know that every exponential curve has a y-intercept at 1. Every one of them does. So for me to get my transformed intercept, then I want to know, where does that intercept get moved to? Where does it get changed to? Where does it get transformed to? So I'm finding the transformed y-intercept. Okay, I'm going to do all of those transformations, but I'm just going to focus in on my transformed intercept. So I need to take that one at 1, and the first thing I have is I need to reflect it across the x-axis. So I'm at -1. I now need to vertically stretch it by a factor of 3. So I stretch it down to -3. I now need to shift it up 4. So if I go up 4 from 3, I land back at 1. There's my transformed intercept. Now, perhaps you like to do that same thing, but you just map out your points a bit. So perhaps what we do is we start with, okay, my y-intercept is at 0, 1, and now I'm going to do those transformations to it. So I reflect that across the x-axis, so that now comes to 0, -1. I vertically stretch it by a factor of 3, so it's 0, -3, and I now shift it up 4 units. That gets me to 0, 1. Perhaps you like to map it out with your coordinates. I don't care how you express it. I don't need to see any work shown. So if you simply wanted to state, okay, I'm thinking about what I'm doing on the graph, and I simply say, okay, my transformed intercept is at 0, 1. You're good. That's all you would have to write down. Okay, I'm going to get rid of that stuff on my graph now. Okay, the last property for us to find is our y-intercept. We know that all exponential functions have a y-intercept, so now I'm going to find my y-intercept. So I know that to find a y-intercept means I sub in x equals 0. And now I can go ahead in my equation. And when I sub in 0 for my x, that's going to give me negative 3 times, well, 2 to the exponent 0 is 1. And if I calculate that, I get back to 1. Now, that shouldn't have surprised you. You had it on your picture from before, but I just found that. So what I can do is I can now take those properties and I can build my graph with it. Take a look at what you need. I need to be able to put on my sketch up to a y value of 4 and also including y values of 1. So I can make my graph somewhat proportional. So the first property that I like to put on is my horizontal asymptote, because that's going to act like a wall, and I know that my graph exists entirely on one side or the other. So I'm going to put on my horizontal asymptote at y equals 4. That means that I know that I can go up to maybe this position, and I can label that at y equals 4. Okay, I also know that I have a transformed intercept at 1. So, somewhat proportional. If my green was 4, then my blue would be about 1 unit. Now, I also notice that my new intercept would be 1. And so it's like my blue and my red both get labeled in the same spot. Okay, I am hoping that we can see that we have one major problem that we walked through. But that would be my process up to this point. We recognize that our major problem is the question finishes by saying, be sure to have 3 features labeled on your graph, and we notice we only have 2. That because my transformed intercept is the same as my new intercept, I don't get 2 distinct points. They lie in the same position. I really just get 1 point. And my problem is I can't tell how steep my graph is with only 1 point labeled. So if we go through in an instance where your transformed intercept is the same as your new intercept, then we need to find another point. And what I like to refer to it as is we're going to find a smart point. Now, the reason why I call it a smart point is because A, we don't want to just pick something random. We want it to have meaning. But we also want to make sure that it can be labeled on our graph easily. So I want to give you an example right now of what I mean by a smart point. We're going to go back and do a good old table of values, but just for 1 point. Let's say that I said, well, I wouldn't mind subbing in x equals 2, right? That's going to give me a point, I don't know, somewhere down here on that line. And I like that for spacing on my graph. That'll help me to connect and create my proper curve. So what I'm going to get rid of is just that dotted line. I'm going to sub in x equals 2. So that means, well, I make that calculation and I now have negative 3 times 4 plus 4. That's going to give me negative 8. And I just want you to notice that on that graph that I have right now, negative 8 would be down here somewhere. I am way off my grid, way off my set of axes. That although subbing in x equals 2 was easy to do, it wasn't a smart decision because it gave me a point off my grid. So that's where I would argue to you that that wasn't really a smart point. Now, there's multiple reasonings for how you get a smart point. I want us to note that that red y-intercept or blue y-intercept, that is my hard turn where I go from being flat to steep. That what I'd like you to choose is a point that I know that I can always label on my graph. So when I go through the process of subbing in an x value, what I'm going to do is I'm going to always pick an x value that takes me closer to the asymptote. So let's consider again, right from the very beginning, what our curve looked like. My base curve was a 2 to the x. I reflected it across the x-axis, stretched it, and now shift it. Notice I have a decreasing curve. So I know if I get rid of all of that stuff, that my curve has to decrease. Therefore, I'm approaching the asymptote up to the left. So what I'm going to do is I'm going to actually pick an x value that goes to the left. I might pick something like x equals -2. Now, you could pick like x equals 1, but my fear might be that those points are so close together, we might not get a great perspective. I really like subbing in x equals -2. So what I'm going to do is I'm going to sub that in. And now I can simplify it. Well, that becomes a -3/4 because 2 to the -2 is 1/4. And now I can just get my common denominator. So that's going to be a -3 plus 16/4. There's a 13/4. I just like you to take a look just at this line for one moment. And notice what that line tells us is we have 4 subtract a bit. So it should make sense then that our solution is a little bit less than 4. And when we look back at our graph, we should be good that our point should be a little less than the asymptote, a little less than 4. Okay, what I now have as my smart point is -2, 13/4. And so I can go and put on -2, 13/4. Now, I'm going to make sure that I mark that maybe somewhere over here. Now, some people are going to have a problem with where I just put that point. And I just want to draw your attention to scale. Some people are going to go, but that's 4 units, according to the way you labeled your asymptote. But you're going to tell me that that's only 2 units? That's not very proportional. And I'm going to tell you, who cares? I'm on a different axis. Remember, that axis changed. So I don't care if I'm not proportional. You clearly can have different scales on individual axes. So I'm just going to get rid of that and say that's what's nice about going towards the asymptote. I haven't defined my x scale yet. So I can pick one that makes my curve look really decent. Okay, the only thing left to do, let's connect everything. Connect your 2 points and approach your asymptote. I get to my transformed intercept, and I have a hard turn, and there is my sketch. Notice what you have, 3 features labeled. You have your asymptote, your transformed intercept, your new intercept, but because those were the same thing, we found a smart point. There is a formal sketch, and that is the process that we are going to go through. Just keep in mind that the only reason why we had to do the purple is because the red and the blue were the same point. That you can only do the purple if your transformed intercept is the same as your new intercept. What I want to spend the rest of our time together today with is, let's make sure that we can knock this out and make it automatic. So let's jump into a couple more sketches and we can make this process pretty smooth. Okay, let's take a look at B. So I want to go through this together, but we're going to do it in bits. We're going to have little pauses. So the first thing that I would always recommend, you take a look at what the base of your function is. It's a base 1/3. And as soon as I see a base 1/3, I know that my base graph would have to be a decreasing curve. So I have that purple in my mind. And now what I want to do is I want to find our 3 features. So let's go in order and we're going to find them on our own. So the first thing I want you to do, I want you to find a horizontal asymptote. So what I want you to do is to go through and write down the equation of your horizontal asymptote. Pause it now. Okay, we're back, and I would hope that I have everybody that wrote down y equals -7. Keep in mind, if you wrote down -7, you're wrong. -7 is a value. We need a horizontal line. It's got to be y equals -7. Okay, you either found that value because you can see that shift on the end, or you took your purple curve and you did all your transformations to it. You reflected it across the x-axis, no change in the asymptote. Vertically stretch it by a factor of 2, no change in the asymptote. Shift it to the left 5. Well, it's a horizontal line. If I shift that to the left 5, no change in the asymptote. The only thing that affected it was the shift down 7. Okay, I can get rid of all of that. Okay, the next thing I'd like you to find is your transformed intercept. So I don't care how you find it, but I want you to now take the old intercept at 1 and find the new position of it. Okay, pause the video now. Okay, I'm going to tackle it both ways, graphically and then through mapping some points. So take a look at our graph. We've got our old y-intercept at 1. I am going to reflect that across the x-axis. I'm now at -1. I need to vertically stretch that by a factor of 2. I am now down to -2. I need to shift that to the left 5. So I am now at the point -5, -2. And I need to shift that down 7. So I would be at -5, -9. There should be the location of your transformed intercept. I'm going to jot that in. There we go. Okay, we could have got there through mapping points, and we could have done the same thing. Well, I started at 0, 1. Now reflect it. Now stretch it. Now shift it to the left 5. Now shift it down 7. Okay, either are good in terms of process. I can get rid of that, and I can get rid of all of these values. Okay, the last thing. Now we can go through and we can find our new y-intercept. And we know to find that means that we have to allow our x value to equal 0. So what I'd like you to do is to go through and find your new intercept. Okay, pause it now. Okay, we're back. So I need to replace my x with a 0. And there's the equation that I get. Now what I have to do is I got to simplify everything on the right side. Okay, I got to follow my bed mass, so I can't touch that -2. I need to simplify my power. So 1/3 to the exponent 5. Okay, that's going to be big. So I've got 1 to the exponent 5 over 3 to the exponent 5. Okay, well, I know off by heart that 3 to the 4th is 81. So if I take 81 and I multiply it by another 3, I'm going to get 243. Okay, here we go. So now let's multiply in our 2. So it's negative 2, 240 minus 7. We're going to stop right there just for 1 second. And notice that what that says is that is negative 7 minus a bit. So we have an idea of where that point's going to exist. It's going to be a little bit below negative 7. Okay, what I want to do is I just want to get rid of that. So as I erase that now, we can go through and we can get our common denominator. That means that I'm going to have a common denominator of 240 thirds. So I get that we're probably pushing buttons on this. And that's going to get us then, when we change negative 7 into 240 thirds, 1,701. And so we get negative 1,703 240 thirds. Now, just keep in mind again that we know that what that is negative 7 and a bit. Like, that's all it is. And you can confirm that. Like, just take 1703 and divide it by 243, and you're going to get, like, negative 7 point, a really tiny amount. Okay, what we've now found are our 3 properties. What we need to do is to put those on our graph. So let's take a look at those properties and what we need to be able to put on our graph to make it somewhat proportional. Specifically all of our y values. So let's look at our horizontal asymptote. We have to be able to show up to a y value of negative 7. We have to be able to show our transformed intercept to a y value of negative 9, and our new y-intercept to a y value of like negative 7 and a bit. The reason why I think it's really important for you to look at those values is because we may be tempted to put our asymptote, since it's at negative 7, somewhere like this. And I'm just going to put a solid line just so we can see it really clearly. I just want you to notice that if I went to view that as my y-intercept at negative 7, it really doesn't leave me much room to be able to see your graph or label any points below that. So, now that we've examined all of that stuff, that might mean that I'm going to choose where to put my horizontal asymptote in the best position possible to enable me to sketch the most of my graph. So, I know it might look weird to you, especially when you see the purple graph. But maybe I'm going to just get rid of that purple graph, and now I'm going to put on what I would deem to be my horizontal asymptote. I'm going to call that y equals negative 7. Notice, by me making that be y equals negative 7, then that allows me to say, well, I have my new y-intercept at like negative 7 and a bit. I also have my transformed intercept at negative 5, negative 9, and maybe somewhere down there. So what I want you to do is to take a look at those features, and let me just make sure I label that, and they would all now be somewhat proportional. Okay. What I want us to do is to take one more key feature, and this is where I want to come back and say, you have the ability to at least check decently on, are those properties correct? So let's take a peek at those 3 properties and let's incorporate one more thing, the direction of my curve. To do that, I'm going to put my purple curve back up. And it's a really sloppy one, but that'll do the job. If I was to take my base function and now do all those transformations to it, Okay, let's reflect it across the x-axis. Vertically stretch it by a factor of 2. Shift it left 5, down 7. Okay, I'm going to get rid of all those graphs now, and I'm going to talk about it in a different way. Okay, look at your original graph, and notice it's decreasing. Well, go back up to your transformations. If you reflect your graph across the x-axis, what does that do to the direction of your curve? And notice, that means I'm now increasing. Okay, I'm going to get rid of that red curve. I don't think we need it. That has changed it to increasing. Well, now, when I vertically stretch it by a factor of 2, does that change the direction? Nope, still increasing. And clearly, when I shift a graph, it's not going to change the direction because by definition, a shift does not change the shape. And so just by looking at those transformations, I can see that my finishing graph should be an increasing curve. Now you look at all the orange points I put down. We know that our graph should be increasing. So I want you to imagine connecting the 2 points you have on your grid labeled and approach your asymptote and see what way that curve has to run. Okay, well, the only way that I can connect my 2 points and approach my asymptote is if my curve looks something like that. And notice, we match up with our increasing curve. So if you went through those 2 points and approached the asymptote, and for some reason they didn't match up, well, then that gives you a little indication that we made a mistake. Now, I'm going to put something on our graph. Our graph is complete, so I want to be very clear with this. But I want you to take a look back up at your transformed intercept. Okay, we're going to look back up at that blue. And I just want us to maybe take a common mistake. I want you to imagine what would have happened if, when we went through and interpreted our transformations in our function, we thought to ourselves that that was a shift to the right of 5. So we made the mistake on what direction we were supposed to shift the curve horizontally. I just want you to imagine then your transformed intercept would have been at 5, -9. Now, what I'm going to do is I'm going to go through and I'm just going to put on my new intercept, my asymptote, and the point 5, -9. And I want you to notice that if I had found those 3 features first, then the only way that I can connect my 2 points and approach my asymptote is if I had a decreasing curve and my check would have told me that I made a mistake somewhere. I could have looked back up and I would have went, oh, shoot, no, that should have been a shift left 5. And I would have been back on the right track. So just as we move forward, I want to make sure that we're good with that as I get rid of all of that purple. That you do have the means to be able to check at least using the direction of your curve. Okay, let's jump into that last problem. Okay, what I would like you to do is to go start to finish on C. So let's find all 3 of our properties first. If you're feeling super confident, then work your way through and start to build your sketch. You know you have a means to check. If you're not so confident, then maybe let's come back after we've found our 3 properties and we should be good. Okay, so I want you to pause it now. Okay, so we're back. So I'm just going to try to keep like the same kind of color coding system. So first thing I'm going to do is find my horizontal asymptote, and I should be good that that has to exist at 4. Y equals 4. Now I'm going to go through and I'm going to find my transformed intercept. That means I need to be able to interpret everything in that equation as transformations. So the first thing I notice is that I'm going to end up dealing with a vertical stretch. So I'm going to take my old intercept that I know always existed at 1 and now deal with a vertical stretch by a factor of 3. That gets me up to 0, 3. Now I can go through and I can move up into the exponent, but I notice that I need to factor out that negative from in front of my x so that that is multiplied by everything on the inside. I'm going to bet and say if you made a mistake on this one, that was probably it. I just want you to note that if you viewed that as being a reflection in the y-axis and then a shift left 1, you will have found your mistake if you use the direction of the curve as a check. Okay, I'm not going to make that mistake, and I'm able to go through. For anyone who did make that mistake, I would suggest pausing it again and trying to finish off the problem again and seeing if we match up in the end. Okay, that reflection is going to have no impact on that intercept. I'm on the y-axis, so to reflect my curve across the y-axis means it did not change. I now shift it to the right 1, and now I finish that off by shifting it up 4. My transformed intercept should be at a finishing position of 1, 7. So I'm just going to get rid of all that stuff. I'm maybe going to keep that factoring in, but I'm going to change the color of my transformed intercept because I can now see it just all in blue. Shift it to the right 1, up 4. Okay, now I need to find my new intercept. So to find my y-intercept, that means my x value has to equal 0. And so when I make that substitution, I'm going to sub it back into the original, not my factored form, because that's going to give me this to calculate. So I can calculate my 3 times 2, there's a 6, add on my 4, there's my 10. Okay, I'm going to plot all my information. On my y-axis, I have to get to a 4, to a 7, to a 10. What that might mean then is when I put on my horizontal asymptote, I'm not going to move that far off the axis. If, let's say, I make that be about 4 units, then I can plot the point at 1, 7 pretty well. And I can put my point at 10. And all that stuff is relatively proportional. Okay, the only way that I can connect all of that stuff is to have a decreasing curve. So I'm going to do my check. Okay, my base of my function is a 2, so I know I'm starting with a rising curve. If I vertically stretch that, that has no change, so I'm still increasing. But as soon as I reflect that in the y-axis, that means I have a falling curve. I'm now decreasing. The rest of my transformations are shifts. Shifts do not change the shape of my curve. I know that I should have a decreasing curve, and that matches with what I have. So the only thing left to do, let's go ahead. My transformed intercept should be a relatively hard turn. And so now I go really flat as I approach that asymptote. Arrows on the end, and we should be good. Okay, hopefully we matched up, and we were pretty solid doing so. My suggestion to you is get used to that algorithm, that process. Find your properties first. Go ahead, put them on your graph. Use the direction of your curve as a check. And just remember that if your transformed intercept and your new intercept happen to be the same thing, then we need to go and find a smart point and just try to be as smart as you can in your selection. Okay, hopefully we're good for today. Job now, jump in and get some practice. Okay, best of luck.